How you doing, Professor?
Hey, Edward. How are you?
I'm all right.
Hang on.
Professor, I had a quick question. I was looking at the live notes section in Canvas,
Yep.
um, and I had like lecture notes for 401, and I was wondering if that was supposed to be there.
Oh, there's lecture notes for 401 in there? Let me see. Oh, that's weird. Yeah, that's not supposed to be there. That's from last semester. Go ahead and delete that. Yeah, thanks for letting me know.
So have you and your fiance started planning stuff yet?
Not really. I mean, with the pandemic and everything, it's been we haven't really started looking, but um, we're thinking about getting just legally married first, just to just because we don't think we're gonna have a wedding anytime, maybe within the next 2 years even. Um, and so we're thinking just get it done at the courthouse, and then we'll deal with it. We'll deal with the wedding after the after the pandemic.
That's what a lot of my friends do.
Yeah, some of my friends have done a virtual wedding actually. So they did um, the ceremony virtually, and they had kind of like they kind of just interacted with people online too. So that was kind of nice. But they had already planned their wedding for like end of 2020, and so of course they had to cancel it. But then that was kind of in place of that because they already had the bride already had the dress and everything, so she wanted to wear it on the day of. So so they had just a virtual ceremony on that day.
That's tough.
Mhm.
When my wife gave birth to our daughter, it was like I couldn't leave the hospital room for 4 days.
Oh
Like
man.
not even to eat. They have like maybe like I have 4 days. I had it like cold sandwiches and salads.
Oh man.
So it was tough.
That sounds tough. Just because no one can come visit in the hospital at all, huh?
No, yeah, no visits. Like my wife had to give birth
Dang.
with a mask.
Oh,
Yeah, it was tough.
yeah, I have a friend of mine who's an OBGYN, and like of course, they try to be careful with masks and everything, but he said sometimes it's really hard to tell, a laboring mother to put a mask on.
Yeah,
But then the whole time he's like, so it's kind of stressful for all the doctors that are in there.
yeah, for sure. It was tough for my wife and me, but
Mm.
it was like I got like cabin fever out there because I'm like going anywhere. Like, it's
Oh, I
crazy.
bet. Yeah. Okay, it's 2:30, so let's go ahead and get started today. Good afternoon, everybody. Welcome to the second class for EGME 407, so week one, second lecture. So how's everyone doing today?
Pretty good. Tired. Had an early morning class.
Yeah, early morning class is definitely, this is I guess not too late, but it's kind of mid-afternoon. But for me, this time is always a little bit rough for me because this is when like I have my mid-afternoon lull. So eat lunch, food coma, and this is usually my time to take a nap sometimes. But thankfully it's not too late, so it's not dinner time after this. So that's good. Okay, so today we're going to be starting our first real lecture, basically. It's cold, yeah. It's been cold. It's been cold lately. And so the subject for today's lecture is going to be conduction. Okay. And so last time, during our course introduction, we talked about the 3 different modes of heat transfer: conduction, convection, and radiation. And so for starting now up until basically the first midterm, we're going to be focusing just purely on conduction. Okay. And so here's our learning objectives for today. And so I have 3. So the first is just to basically just describe the factors that will affect heat transfer. Second is we'll talk about a certain property that all materials have, called its thermal conductivity. And we'll discuss what that is and how we can rank that among different substances. And then for the rest of the lecture, we're going to be talking about the heat equation. And so what it is, how we get there, and how do we actually use it to solve for the temperature distribution. Okay. And so this mode that you see right now, this is kind of the usual lecture mode where last time, I prepared lecture slides just because, there was, a lot of pictures that I wanted to show you. But usually, for the lectures, just to kind of emulate the whiteboard, I have basically my iPad right here. And I'm going to be writing notes on this iPad that'll be streamed through Zoom kind of in real time. Okay. And so one thing I'll say is that my writing on the iPad isn't the best. In fact, it's pretty bad. A lot of times I look back on my notes and I don't even know what I wrote sometimes. And so, at any time, if I write something down and you can't read it or anything, just let me know. You can even interrupt me and just turn on your mic and say, I don't know what that says. And I'm always happy to kind of rewrite stuff and clarify, because sometimes I'm writing stuff and I'm kind of in the flow of the lecture, and sometimes I don't notice these things. So just shout it out and let me know when something's not clear. Okay. Okay. So are there any questions on anything before we get started? Okay. All right, so let's get started with conduction. All right. And so first thing, let's recall our definition of conduction that we went over last time. Okay. And so the definition, conduction is the transport of energy in a stationary medium due to a temperature difference. Okay.
Professor?
Yep, what's up?
I just have a quick question in regards to the assignments.
Yep. Mm-hmm.
Yeah, I was just wondering, like, the frequency of them and when are they going to be posted and when are they usually going to be due?
Yeah, that's a great question. So the homeworks, I always give you at least, a week to do them. And so the next homework assignment, usually I don't stack homework assignments. So if you're working on one, I don't give you the next one until that one is turned in. And so my plan right now is to give you the next homework assignment on Monday. And it's going to cover stuff from this lecture and the next lecture on Monday. And then you'll have a week to turn that in. And so the next homework will be assigned on Monday of week 2, and it'll be due on Monday of week 3. Yep.
I understand. Thank you.
Mm-hmm. Okay. And so if you have, a stationary, what I mean by a stationary medium is just any kind of substance that isn't moving, okay? Because as soon as you have something that's moving, then we're in convection. But since we're in conduction, things are staying still. And so anytime you have a temperature difference between, 2 points in let's say a solid, then we have conduction, okay? Okay, so the first formula that we'll introduce with regards to conduction is known as Fourier's law, okay? Fourier, it's spelled like Fourier, but I guess he's French or something, so it's pronounced Fourier. Okay, and so Fourier's law is given by the following. Okay? And so we have Q sub x is equal to minus K times A times dt dx. Okay, right? And then let's define all of these terms right here. Okay. So first, let's start with Q sub x. And so Q sub x here, this is our heat transfer rate. Okay. And so the typical units for Q are going to be watts. Okay. And so Q sub x is basically a unit of power. So it's basically how much energy is being transported per unit of time. Okay. Okay. Next, we have thermal conductivity, which is our K. And so we'll get into this more later, but basically you can think of this as a parameter, a physical parameter of your medium that determines how easily heat moves, okay? And the units for this are going to be watts per meter and degrees Celsius, okay? So those are the typical SI units for that. So you have watts on top, and on the bottom you have meters, which is a unit of length, and then times degrees centigrade. Okay. Okay. And so A right here, this is our cross-sectional area. Okay. And in particular, this is the area that is perpendicular to the direction of heat transflow. Okay. And typical units for area is pretty standard. So we're going to use the SI units, meter squared, or of course it could be centimeters squared or inches squared, something like that. Okay. Big T, and so big T right here is just going to be temperature. Right. And so typical units of temperature that we'll use in this class are going to be degrees centigrade, or Kelvin. Okay. So Kelvin, I think, is typically used more in thermo, but in heat transfer, we can actually use either or, Celsius or Kelvin. Okay. Right. And then this this derivative that we have here, dt dx, this is known as the temperature gradient. Okay. Okay. And so what this is basically how quickly the temperature changes over a certain distance. And we'll define that more on the next page. Right? And so typical units for temperature gradient are going to be temperature over length. And so we have, let's say, degrees centigrade or degrees Celsius over meters. Okay. Right. So here's our Fourier's law and all of the parameters that go into it. And so what we're going to do next is we're going to go basically into each of these parameters and show how they affect heat transfer. Okay. So before I do that, are there any questions on this?
What's temperature?
So temperature is just how you kind of you interpret temperature. So whether something's hot or cold, right? So the more hot something is, the higher temperature is going to be. But more specifically, I guess temperature kind of is a way for you to assess how much energy that object has, right? And so typically objects that are really hot, we say that they have a lot of what's called internal energy. And so those are objects that are more energetic. And so that's why, when we say conduction is the transfer of heat from something that's hot to cold, then that means basically energy is transferring from the hot surface to the cold surface. Yeah.
That was supposed to be a joke, but
Okay. We're still getting to know each other, so always take things seriously until then. Okay. And so let's go into this a bit more. So let's do just kind of a simple example, just kind of illustrate this. Okay. And so let's say that we have a tube. Okay. And so we have T1 on one side and T2 on the other. Okay. And then let's say that on the sides of the tube are insulated. Okay. So you'll hear the term insulated quite a bit in this class. And so all insulated means is that there's no heat transfer that can occur through that surface. Okay. And so if we have the situation where T1 is greater than T2, okay, then what this will basically mean is that heat is going to flow from left to right. Okay. Okay. And so the direction of heat transfer will be this way. Okay. And so, the sides being insulated is really important because normally if you have a tube like this, you can have heat that escapes out the sides. But, if you insulate the outsides, there's really only one direction that heat can go, which is from left to right. Okay. And so that's basically what Fourier's law says, that if you have a temperature gradient where basically you have a difference in temperature over a certain length, okay, then heat transfer will occur. Okay. And so that kind of explains the temperature gradient part of Fourier's law. Right? Question. So question in the chat. Is truly insulated even possible, similar to frictionless problems? Yeah, that's a great point. And so you're right. So having something be perfectly insulated is never possible, right? So there's, anytime you have a pressure difference, a temperature difference, no matter how much you insulate it or what kind of crazy materials that you put into it, there's no way for you to block all the heat transfer. But, it's an assumption that we make often in problems because practically speaking, you can get close enough to perfect insulation. Whereas, let's say that this insulation right here, maybe it's not perfect, but if you compare the amount of heat that's escaping the outside compared to the heat that's going through the cylinder, the one that's going through the cylinder is a lot higher, such that we can ignore the ones coming out the outside. But that's a great point. So perfect insulation is never possible. Mm-hmm. Okay. So that's the temperature gradient. And so now let's look at the other factors that will affect our heat transfer. Okay. And so let's start with the area. Okay. Right. And so the area in my little diagram up here might be like the circle that you can kind of slice through this cylinder. Okay. And since, if we go back to Fourier's law right here, since area is on kind of this in this form in the equation, what this tells us is that, if we have a higher area, then we're going to have more heat transfer. Okay. Okay. And so this is pretty intuitive. So like if you have a small tube compared to a large tube and you expose both of them to the same temperature difference, right? So you compare kind of these two situations. Okay. The tube on the right here is going to have more heat transfer just because there's just more space for the heat to go. Okay. And so one way that you can kind of minimize heat transfer in certain situations is if you don't want heat to go a certain way, it's just to kind of minimize the amount of area or minimize the amount of contact that you have in those places, right? Let's see, comment in the chat. So the comment in the chat says is that there was a video where a material was heated up to 2,300 degrees and a guy grabbed it with his bare hands because the material was a very poor heat conductor. Yeah, that's definitely possible. So there's, there's a lot of materials out there that are really terrible heat conductors. So even if it is something that's really hot, you can still grab it and, very little heat will actually come to your hands and you can actually be safe. So, a lot of those kind of really crazy materials are used in like aerospace applications because, re-entry, kind of like what you mentioned, incurs a huge amount of heating. And so, that's actually one of the really cool applications of heat transfer is how to design, re-entry without the whole thing just melting on itself. Yeah, space shuttle tiles definitely use the same thing. Anything you're leaving the atmosphere, coming back in, you're going to have a ton of heat transfer. Okay. Okay. Any questions on this so far? Okay. All right. So let's talk about. Actually, let's come back to the temperature gradient again, and then specifically, let's talk about the dx. Okay. And so our temperature gradient is given by this this expression here. Let me rewrite it. Okay. And in particular, let's look at the bottom. Okay. And so this dx right here represents any kind, basically some kind of horizontal distance. Okay. That the heat must travel. Okay, and so once again, let's draw two situations, and then let's talk about them. Okay? So let's say that we have one tube, and let's say it's a long boy, right? Okay, and then let's draw a shorter tube as comparison. Okay, and once again, the two ends of these tubes are exposed to the same temperature difference. Okay, all right. And so let's consider this one first on the left. Right? And so in this situation, we have our temperature difference. So heat is going to flow this way, but because we have a fairly long tube, the heat transfer doesn't have to be that high in order to basically achieve this temperature drop. Okay. Okay. Whereas if you compare it to our case on the right, our horizontal distance here is really small, right? And so in order to basically make sure that the temperature drops from T1 to T2 in that time, the heat transfer here has to be much bigger, okay? And so, if we compute this quantity right here, or we compute an approximation for it, right? And so an approximation for this could be like T1 minus T2 over the length, right? And where the length will be kind of this distance right here. Okay. And so even though both cases have the same temperature difference, the second case here will have a much higher gradient because the length is shorter. Okay. Okay. And so, this horizontal distance matters a lot. So, temperature difference, ultimately that's going to be the thing that drives the heat flux or the heat transfer rate But the amount of heat that actually gets transferred also depends on that distance too. Okay, and so I want you guys to always kind of keep that in mind when we're doing our problems. Okay. All right. Any questions on this? Nice. Yeah, I'll check out that video later. Yeah, thanks for sharing that. Okay. So those are the two big things I want to talk besides the thermal conductivity. And so next, let's talk about that, because that one's actually really important. Okay. Okay. All right, so let's define this. And so the thermal conductivity, this is a property of the material. Okay. Okay. And so when I mean property of the material, it means a property of its basically chemical compounds, right? So things like aluminum will have a certain conductivity, or ceramics will have a certain thermal conductivity. Okay. And so what the thermal conductivity represents is it reflects, it represents how easily heat can move through these materials. Okay. Okay. And so what this is a function of, and a lot of times, the way that we determine thermal conductivity is we simply just have to run experiments on it. So there's been a lot of tests that have been done over the years about, what is the thermal conductivity of like aluminum. And so they run an experiment, and then they measured how much, they put a temperature difference, they measured how much heat was transferred. And then from there, we determined K. And the reason for that is the main determining factor for K is actually the molecular structure, or the how closely packed the atoms of that material are. Okay. And so in general, what you can kind of expect is that the more closely packed the atoms are, and the better organized they are, the more easily heat's going to transfer. Okay. Okay. And so let's talk about kind of the relative thermal conductivities for certain materials. Okay. And so most of the times, if you're doing any work on heat transfer, you just look these up in a table or any kind of material data sheet. But there are some general trends that we can talk about. Okay. All right. And so first, let's talk about solids, liquids, and gases. Okay. Right. And so generally, what you'll observe is that solids have much higher thermal conductivity than liquids, and liquids have much higher thermal conductivity than gases. Okay. And the reason for this is that solid, because something is a solid, their molecules are really closely packed together. Okay. Okay. And so if you kind of took a microphone and you zoomed in on a solid, you'd see a bunch of molecules that were kind of closely packed like this, right? And because, you know, conduction is essentially energy transfer between neighboring molecules or neighboring atoms, it makes sense that, you know, if your molecules are packed close together, it's much easier for them to transfer energy, okay? Whereas if you compare that for a gas, you know, in a gas, the molecules are there, but there's a lot of empty space between them, okay? And so you might have, you know, molecules that kind of look like something like that, right? And they're all kind of flying around, okay? And so that's why gases tend to have the lowest thermal conductivity, just because the atoms just don't interact with each other enough to transfer heat, okay? And liquids are somewhere in between that. So liquids, you know, generally the atoms are pretty well packed, but, you know, there's still some space because they can move past each other pretty easily, okay? And so generally, you know, if you are considering a solid, a liquid, and a gas, you know, solids have the highest thermal conductivity, while gases have the lowest, okay? Okay, any questions on this? Okay. All right, and so the other one I want to talk about is let's take solids again, because, you know, we're going to be focusing mostly on solids here in the conduction unit. And so let's talk about metals versus nonmetals, okay? Okay. And so generally what you'll see is that metals have a much higher thermal conductivity than nonmetals, okay? Because what are metals known for, at least in terms of their molecular structure, right? Metals are known to have very organized and very structured molecular structures, okay? Okay, at least much more so than nonmetals, okay? And so generally what you'll see is that, you know, metals will conduct heat really, really easily, okay? And so if you take like a copper rod and you heat up one end, the other end will heat up very quickly because the thermal conductivity is really high, okay? And so this is kind of the reason why, you know, when you're designing devices that are meant to hold hot things, like let's say like a coffee mug, right? So I have my coffee mug right here, okay? And so this coffee mug is made of ceramic, so it's not made of metal. Because if it was made of metal, as soon as I pour hot tea into my coffee mug, I couldn't grab it because, you know, the heat would conduct through the whole thing really quickly, right? And so metal, that's why kind of metal coffee mugs are not really a thing, because, or at least not to hold anything hot, because everyone would just burn their hands all the time, okay? Yes, yes, copper core pans, definitely. So yeah, so there's a lot of cooking devices which have copper cores because copper conducts heat super, super well. And so in situations where you want heat to disperse and really easily, copper is definitely a good way to go, okay? Okay, and so that's the thermal conductivity. So, you know, of course, you know, the things that I just mentioned, these are just the general trends, but even among like metals, there's a huge amount of variability with them. And there are some nonmetals out there that have higher thermal conductivity than some metals. So, you know, what I just mentioned are just kind of general trends, but there are, you know, certainly a lot of exceptions to the rule, okay? Okay, so I do want to mention a couple other properties, which we won't do anything with them now, but in a few weeks when we go to transient heat conduction, we'll come back to it, okay? And so the first one is specific heat. Okay. And so specific heat is another physical property, and this one basically tells how well the material can store energy. Okay. And so it's a bit different than thermal conductivity, because conductivity basically defines how well heat can move through a material, right? Specific heat will tell you how well that material can kind of hold on to that thermal energy, okay? And so I'll bring up a lot of examples from cooking, because that's kind of what I'm really into, okay? And so if you've cooked for a while, you know that there's a certain kind of pan that you can have called cast iron, okay? And everyone loves to use cast iron for everything. And the reason, there's a lot of reasons people use cast iron, but one big reason is that it has a very high specific heat, okay? And so basically what that means is that once you heat up a cast iron, it stays really hot, right? And so it'll take a while for it to cool down. And so when you try to put meat or any kind of food onto the cast iron, it'll stay really, really hot, okay? And that's different from, let's say, like a nonstick pan, or maybe a more flimsy pan, where it might be really easy to get it hot, but as soon as you put something in the pan, it cools down really quickly. So it's maybe not as good for searing meats or anything like that, right? Yes, cast iron does stay hot forever. Yep. All right, question. So is that constant through phase change, like going from solid to liquid? Yeah, that's a good question. So usually these physical properties do change, as you change phase, and there are actually a lot of these properties are actually functions of temperature too, and so they, a lot of them don't stay constant when you go through phase change, but there are some that do. So it really kind of depends on the material. But generally, when you change phase, you kind of are changing the molecular structure of the material. And so, from going from a solid to liquid, you're putting in a lot more movement between the molecules. So in that sense, that kind of changes, what these like macro properties, or, thermal properties that we observe. Yeah. Mm-hmm. What's one that stays the same? It's hard to speak in absolutes, because I don't know every single material out there. And so I don't have one that comes to mind, but I imagine that there might be some out there, because I haven't heard of someone say that this is absolutely the case, that it always changes in phase change. But I'd have to look it up, and I'd have to see. Yeah. Mm-hmm. Okay. And then, so that's specific heat, okay? And so one thing that's related to specific heat is heat capacity. Okay. Okay. And so these guys are kind of two sides of the same coin. And so this kind of relates the same thing for how much heat that a material can store. It's just that the way you compute it is different. So the symbol for specific heat is given by C sub P. And so the way that you compute heat capacity is you just multiply it by density, okay? Okay. All right. So that's heat capacity. And then there's one more thing I want to mention, and that's the thermal diffusivity. So again, we're not going to be doing anything with this, at least for now, but we will in a few weeks, okay? And so thermal diffusivity basically describes how quickly a material can respond to changes in temperature. Okay, and then the symbol for thermal diffusivity is alpha, and then the way that you compute it is that you take its thermal conductivity, K, and then you divide it by its heat capacity. So you divide it by rho times Cp. Okay. And so materials with high thermal diffusivity, if you heat them up, they heat up really quickly. Whereas materials with low diffusivity, it's going to take a while for them to heat up. And that's a function of both, how well can heat move through the material. That's why thermal conductivity is there. And it's also a function of how much heat it can store, which is why heat capacity is there. So it's kind of almost like the ratio in between the two. Okay. Okay, any questions on this? Okay. Okay, so those so that kind of covers all of the the properties at least for now that we'll talk about. So now let's actually talk about how do we actually start solving some heat transfer problems. Okay, and so the first starting point is just the heat equation. Okay. Okay. All right. And so we've already seen one equation, which is the Fourier's law. Okay. And so that relates heat transfer rate to temperature gradient. But usually when we're performing thermal engineering, what we want to know actually is we want to know what the temperature distribution is in our material. Okay. Okay. And so Fourier's law comes into the heat equation, but the heat equation is usually the one that we actually solve. Okay. And so, if you just took fluids last semester, or, you still have fluids, some fluids background there, the heat equation is kind of like the Navier-Stokes of heat transfer. Okay. But it's a lot easier to solve. So it's not as difficult as Navier-Stokes. Okay. Okay. And so what the heat equation basically shows is, how heat is spatially distributed. Okay. And so the physical mechanism through which heat actually moves through a surface through conduction is a mechanism called diffusion. Okay. Okay. And if you haven't heard the word diffusion in a previous class before, basically diffusion is just passive spreading. Okay. Okay. And so the analogy that I like to give with to illustrate diffusion is, say that you spray some air freshener into the air, right? And so let's assume that you're sitting in a room where there's no wind that's blowing. Okay, so the air is perfectly passive. And so if you spray air freshener into the air, generally what you expect is that eventually someone sitting on the other side of the room will smell the air freshener. Okay, it might take a while, but eventually it will go there. And that's done all through just passive spreading. So there's no wind that's blowing or anything like that. And so diffusion is just kind of just the tendency for, things just to kind of spread out passively. Okay. And so just to kind of give you a kind of visual representation of this, right? And so let's say that, we have something that looks like this. Okay. And so let's say that this is, you just sprayed air freshener. And so you have peak air freshener kind of right above you. And so after some time has passed, that air freshener will kind of spread throughout the room, and it'll spread kind of equally in all directions. Okay. And so after diffusion has occurred, your air freshener might look something like this. Okay. And so it's kind of spread throughout the room. Okay. Okay. And so heat basically transfers in the same way. So heat is basically going to passively spread through your material. And that's what the heat equation is basically going to show us. Okay. All right, so I'm not going to go through the whole derivation of the heat equation just because it's kind of long and stuffy and I think not that useful. And so I'm just going to give you guys just the equation for it. But I will talk about, if you do want to derive it, where you would go. And more importantly, what do each of the terms in the heat equation mean? Okay. Before I do that, are there any questions on this? Okay. Okay, and so let's write out the heat equation. Thankfully, it's a lot shorter than Navier-Stokes. Okay, and so first we have the partial derivative t, second derivative with respect to x. Okay, second derivative plus a quantity that's q dot over k, and I'll define what this is in a second. Okay. And this is equal to 1 over alpha. Remember, alpha is our thermal diffusivity, and then partial t. Okay, and so that last term is the derivative of temperature with respect to time. Okay. 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 So let's talk about each of these terms individually. Okay. And so first, let's talk about this guy. And so this is a second derivative of temperature with respect to space, okay? And so this term basically governs how the temperature varies in space. Okay. And so I say space here because, our derivative here is with respect to x, right? And x in our case is usually used to denote some kind of distance, okay? And so since this is a derivative of temperature with respect to distance, then this derivative right here basically shows that, okay? And so this is our diffusion term, which I talked about before. Right, and so what we're going to do soon is we're going to start solving this. And just like if you kind of remember how we did Navier-Stokes problems, we canceled out some terms due to assumptions. But this first term that I've circled here, this guy always stays. So no matter what assumption that we make, this guy is always going to be there. Okay. Okay. And so next, let's do the second term, which I've circled in green. Okay. And so this guy. This represents thermal production. Okay. Okay. And so what that means is that any thermal energy that's created in the system basically will be accounted for in this term right here. Okay. Okay. All right. See a question in the chat. Okay. All right. Question. So in 3D, do we just write 2 more PDEs for the other 2 directions? And will we do that in this class? Yeah, that's a great question. And so, Kate made a great observation where this is just the 1D heat equation. And so in 2D and 3D, there's what you actually do is you add more derivatives to this. And so what you would have here is you would have another derivative, second derivative with t with respect to y, and then another derivative with t with respect to z. And so there's only one heat equation because temperature is just a scalar value. So you only need one equation to solve for that unknown. But when you get into 2D and 3D, you just add more spatial derivatives to this guy. Yeah. We're not gonna do that in this class explicitly because solving a PDE is really challenging. But we will talk about some approximate methods that you can use to solve for those kinds of problems. But we're not going to be solving the 2D or 3D heat equation exactly. That's you need to take a PDE class for that, which is kind of beyond the scope. Yeah. Okay. So this thermal production term, it can be a little bit misleading because, you know, everyone knows, you know, energy can't be created or destroyed. But the key here is thermal energy. Okay. And so within the context of heat transfer, you can convert energy from a different form into thermal energy, right? And so let's take an example inside your car, right? And so inside your car, you know, you put gasoline in your car to help you move, right? And so what your car is doing on a regular basis is that it's basically turning that gasoline, which is basically energy in chemical liquid form, and then it's transforming that into thermal energy, okay? And so strictly from just a heat transfer point of view, whenever you basically burn gasoline, then you have thermal energy that's being produced because it's being converted from a different form. And so we can't spontaneously create thermal energy, but we can convert to it from a different form, okay? Okay, and then the last term right here, which you know, for most of this next couple of weeks, we're going to assume is 0. This is our unsteady term, okay? Okay. And so the unsteady term basically describes how energy can be stored within the medium. Okay. Okay. And that's why we have our thermal diffusivity there in front, because that's kind of what describes it. Okay. Okay. And so this is the heat equation here. So again, you know, I've skipped over the derivation, but if you wanted to, if you are interested, you know, it's definitely outlined very well in the book, so you can definitely look there. But just in a nutshell, the way that you would derive this equation is to apply conservation of energy to basically a really tiny element, and then you kind of, you know, work your way from there. So if you're interested, you know, we can definitely talk about it outside of class. But just for the purposes of just, you know, just so we can do some examples, I'm going to skip through that derivation. Okay. Okay. So this is our heat equation here. And so right now we actually can't solve it because there's kind of too many terms. And so the way that we actually go about solving this is we have to apply some assumptions. Okay. Okay. And in particular, you know, there are two main assumptions that we're going to make. Okay. Right. The first assumption, which will always apply, at least for now, is we're going to assume steady state. Okay. And so when we assume steady state, what that basically says is that any time derivative is going to be equal to 0. Okay. And so when we make the steady state assumption, we can cross out the time derivative with respect, or the derivative with respect to time. Okay. And so that gets rid of that term. Okay. Okay. And so we basically are almost always going to make this assumption until we get to transient heat transfer. But I'll let you know when we get there. Okay. Okay. Another assumption that we'll often make, which will sometimes be the case, but not always, is we assume that production is going to be 0. Okay. And so when we make the no production assumption, we can go ahead and cross out the green term right there. Okay. And so this happens pretty often. Usually the problem will explicitly tell you that there's some kind of thermal production. But if it doesn't say anything, or if the problem says you can assume it's 0, just go ahead and cross that out. Okay. Okay. So then what we're left with after doing all that is just our red term right here, okay? Okay. And so this is actually a pretty simple, differential equation to solve, because we basically have the second derivative of t with respect to x is equal to 0, okay? Which I'll write on the next page. Okay. But before I go there, are there any final questions on this page here? Okay. Okay. And so what we're usually left with after making those two assumptions is this guy. Okay. All right. And so this is it's technically a differential equation. And so the way that we can solve for this is we can just simply integrate it twice. Okay. And so let's go ahead and do that. And so we perform this integral once with respect to x. And so the left-hand side becomes dt dx. Okay. And so we get rid of one of the derivatives. And then on the right-hand side, what we get is just an arbitrary constant. And so we just get c1. Okay. Because we integrate 0, normally we get 0, but because we're doing indefinite integrals, we need to add a c1 over there. Okay. All right, and so we're not done yet. And so we need to integrate this one more time. Okay. And so we integrate this one more time. On the left-hand side, we get t of x, which is good. Okay. And then on the right-hand side, we're going to integrate c1, where c1 is just a constant. And when we integrate that constant, we're going to multiply it by x. Okay. And then to that, we're going to add c2, which is a second arbitrary constant. Okay. 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 And so that's the temperature solution, but we're not done yet because we have to actually solve for this C1 and C2. And if you remember from either 308 or maybe fluids, the way that we solve for these constants is we have to apply boundary conditions. Okay. And so for heat equation problems, there's 3 types of boundary conditions that we can specify, which we'll go through right now. And so let's go through the types of boundary conditions that we can solve, that we can apply, and then we'll do an example problem that kind of pulls all this together. Okay. And I hope we'll have time for a second example too. Okay. Okay. And so the first type of boundary condition that we can specify is a constant temperature, or I should say a specified temperature. Okay. Right. And so this is kind of the simplest boundary condition that you can have. And basically what this says is that, one surface in your medium at the boundary is maintained at a known temperature. Okay. And so mathematically, the way that you would apply this, and let's say that our known temperature is T naught. Okay, so we'll say T0. And so, and let's say that this is known at X naught. Okay. And so the way that you would apply this boundary condition is you would plug in X is equal to X naught into your differential equation, and you set that equal to T naught. and then you use that to solve for one of the constants. Okay. Okay. Any questions on this?
Professor?
Yep. Mm-hmm.
So that would be like on the example where you had like the tube, like T1 and T2.
Mm-hmm.
Those would be like the specified temperatures, and then the locations would be like relative to whatever coordinate axis you set up.
Exactly. Yeah. Yeah. So that tube is a great example where we have two specified temperatures. So let's say that on the left-hand side, we have x is equal to 0. And the right-hand side, we have x is equal to L. And so you would do T at 0 is equal to T1, and then T at L is equal to T2. Yeah. Mm-hmm. Okay. So that's the first type of boundary condition. The next one is a specified heat flux or heat transfer rate. Okay. Okay. And so in these situations, you're going to specify not the temperature, but how much heat is going through that surface. Okay. Okay. And so for this, we're going to use the equation that we started with today, which is Fourier's law. Okay. All right. So this has two different forms. And so let me show you kind of both of them here. Okay. So the first form is if you have a specified heat transfer rate, you would just use Fourier's law. Okay. Okay. And so remember the units for heat transfer rate are watts. Okay. And so to apply this boundary condition, you would take your temperature distribution with the constants, you would take its derivative, and you would set it, you set x is equal to wherever the the heat transfer boundary conditions taking place. Okay. You multiply it by k, you multiply it by a, and then you set it equal to the heat flux or the heat transfer rate. Okay. Okay. And so the other form that this would take looks very similar, except the only difference is that we have quotation marks next to the heat transfer rate. Okay. And so what this means is that this is no longer a heat transfer rate, but this is a heat flux. Okay. And then the other thing you'll notice is that area is missing from the right-hand side of the equation. Okay. All right, question. So is heat transfer rate the same as Q dot or dQ dt? Ooh, yeah, that's a good question. Let me look ahead in the notes a little bit. I believe Q dot has units of watts over meters cubed. Let's see. Yeah, Q dot actually has units of watts over meters cubed. So it's actually Q divided by volume. Yeah, yeah, we'll get to that. So we'll do an example with Q dot so you can see that. Mm-hmm. Okay. And so heat flux here, the units for this is watts per meter squared. Okay. All right, so I want you guys to be careful when applying this type of boundary condition here. So if the problem gives you heat transfer rate, then you have to include this A right here, okay? But, if the problem tells you, it's giving you heat flux, then you keep it without the A. So you use this form right over here, okay? And so it's a subtle difference. So, it's definitely something to be careful about, okay?
So sorry, for heat flux, was that QX double prime?
Yes, it's QX double prime.
Okay, thank
Okay, and so a common special case for this, which we've kind of already seen, is if your surface is perfectly insulated, or another word for that is adiabatic. Okay, and so in those cases, the heat transfer rate or the heat flux is going to be equal to 0. And so again, it's impossible to get perfectly 0, but for practical purposes, it's normally okay. Okay. And so that's kind of a special case for this type of boundary condition. So sometimes it won't tell you that the heat flux is 0, but if the problem says that this surface is insulated or this surface is adiabatic, you can basically apply a zero heat flux boundary condition there. Okay. All right. Are there any questions on this? Okay. And so there's one more type of boundary condition I want to go over before we do an example, and that's a convection type boundary condition. Okay. Okay. And so I know that we're in the conduction unit, but oftentimes, we're going to be faced with problems where we have convection that occurs on the outside. Okay. And we can actually, use this as a boundary condition. Okay. And so these are unfortunately the most complicated boundary conditions. So the formula looks like this. Okay. And so on one side, you're going to have basically Fourier's law. Okay. Okay. And so we have minus k times dt dx at x is equal to xb. Okay. And so that's basically the conductive heat transfer. And on the right-hand side, we're going to have the heat transfer due to convection. Okay. And so the way that we describe this is using Newton's law of cooling, which we saw briefly in the introduction slides last time. Okay. Right. And so this will be H, where H is our convection coefficient, which will always be given to you. Okay. Right. And that's going to be times T infinity, where T infinity is the ambient fluid temperature. And then from that, we're going to subtract the temperature at the surface. Okay. And so visually, it looks something like this. Okay. And so on one side, you have your solid. Okay. On the other side, you have your moving fluid. Okay. And so the moving fluid usually is denoted by some arrows. This is just to show you that fluid's moving there. Okay. And then at the surface, we're going to have our temperature here. So we have T of x, b. Okay. And this right here is our boundary. Okay. And so what this boundary condition basically says is that the heat that's lost from the surface due to conduction. Okay. The heat transfer due to conduction has to be the same as the heat that's absorbed into the fluid due to convection. Okay. And so when you have a convection boundary condition, we're basically saying that, the conduction and convection have to be the same at that boundary, basically because of conservation of energy. Okay, so any energy that crosses out due to conduction has to be accepted due to convection, and then the other way around too. So if you have like a hot fluid, the heat transfer that goes from the fluid to the solid, both the convection and the conduction calculations have to be the same. Okay. And so we'll do an example with this one just because it's probably not today, but probably next time that kind of shows that, because it can be a little bit tricky to apply. Okay. But are there any final questions on this before we do an example?
Where you have the solid and moving fluid separated, does that correlate to the left and right hand side of the convection boundary condition equation, or is that just
yes? Yeah. So the solid, I put the solid on the left hand side to correspond with the Fourier's law on the left, and I put the moving fluid on the right to correspond to the convection side of that boundary condition on the right. Yeah. Mm-hmm. Okay. So let's do kind of a simple example just so you can kind of see the heat equation in action. Okay. Okay. Cool. Okay. And so let's say that we're designing a window pane. Okay. Okay. And then on both sides of the window pane, we know both temperatures. Okay. Okay. And so let's draw the schematic for it. Okay. And so, we're basically looking at a cross section of our window. Okay. So let's say, you have your window, you turn it so that it's like this, and then you're looking at it like that. Okay. And so on one side, we have this is inside. On the other side, we have outside. Okay. And so on the inside, we have a temperature Ti. And the outside, we have TO. Okay. And then the width of this window pane will be L right here. Okay. Where this on the left-hand side, we'll call this x is equal to 0. And on the right-hand side, we'll call this x is equal to L. Okay. Okay. And so from this problem, what we want to do is we want to solve the heat equation. For the temperature distribution in the window. Okay. All right, so there's our problem statement. And then let's state our assumptions, okay? And so we're going to assume that there's going to be no production. And we're also going to assume steady state. Okay? And then our boundary conditions. In this case, we have specified temperatures on both the left and the right. So let's go ahead and list those out. Okay. Okay. And so at T at x is equal to 0, we're going to have TO. Okay. And then T at x is equal to L, this is going to be TI. Okay. And so from here, we're basically going to start with the heat equation, integrate it twice, and then use the boundary conditions to solve for the constants. Okay. All right. Any questions on this before we go about solving this? Okay. Whoa. Oh, that's weird. Okay. And so let's start with our full heat equation. So we have d squared t dx squared plus our q dot over k is equal to 1 over alpha partial t partial time. Okay. Okay, so let's apply our assumptions here. And so the first thing we assumed was that we have no production. Okay. We also assume steady state, so we can go ahead and cross that guy out. And so once we apply those assumptions, what we're left with is just d squared t dx squared, okay, is equal to 0, right? Which we've seen before. So this was kind of the one that we actually integrated. Okay? And so if we integrate this twice, right, what we're left with is t of x is equal to c1x plus c2. Okay. All right. So same as kind of the derivation that we were working with before. Okay. Okay. And so now what we can do is we can start to apply boundary conditions to solve for C1 and C2. Okay. Okay. And so first, let's apply the boundary condition at x is equal to 0. Usually that's a good one to start because that's usually a little bit easier. Okay. All right. And so at x is equal to 0, we have t of 0 is equal to t o. Okay. Okay, so let's plug in 0 into our equation up here. Okay. So t of 0 is equal to c1 times 0 plus c2. Okay. And this is equal to to. Okay. Right. And so in this equation, we have c1 times 0. And so c1 times 0 is just going to be 0. And so what we're left with is c2 is equal to t0. Okay. So that's great. So that's one of our constants. Okay. And so now let's apply the boundary condition at x is equal to L. Okay. And so at x is equal to L, okay. At x is equal to L, we have t of L is equal to ti. Okay. And so let's go ahead and plug in L into our t expression. Okay. So we have t of L is equal to c1 times L, okay, plus c2, but we already solved for c2, so c2 is just to. Okay. And so this is going to be equal to ti. Okay. Okay. And so from this expression, we can solve for c1. Okay. And so we'll subtract t0 from both sides. And so we have c1 times L is equal to ti minus to. Okay. And then we divide both sides by L. And so we get c1 is equal to ti minus to divided by L. Okay. Okay. And so now that we have C1 and C2, we can go ahead and plug these back in and solve for the final temperature distribution. Okay. Okay. Any questions on that before I write out the final solution? I can wrap up for today.
How did you know that it's equal to TI?
Yeah. So that's
Is that just arbitrary?
Yeah. So that was just kind of that was just kind of how the problem was defined. So the way the problem was defined, the boundary conditions were specified temperatures both on the left and the right. And so when we plug in x is equal to L, then we have this temperature Ti on the right-hand side. Yeah. Yeah, so usually the problem will tell you, what boundary conditions that you should apply. Mhm.
Okay, that makes sense.
Okay, and so when we plug in for C1 and C2, we get T of X is equal to Ti minus To all divided by L times X plus To. Okay. And this is our temperature distribution. Okay. Okay. Okay, so it's 3:45, so that's all we got time for today. And so next time we'll do another example just so you can see a little bit more complicated boundary conditions and how to deal with those in the heat equation. And then from there, we'll start talking about thermal resistances, okay? Okay, so thanks guys for tuning in this week. This is our first week of lectures, so we have the rest of the semester to go. So thanks for tuning in. Have a great weekend, and I'll see you guys on Monday.
Yeah, have a good day, Professor.
Thanks,
Yes,
guys.
you
Have a
too.
good
Thank
weekend.
you.
A good one, Professor.
Thanks.
Thank
you.
you.
Too.
Thank you, Professor.
Mhm.